Good morning. Today we are going to solve some problems to reinforce the concepts of electric field that we discussed. So I'm going to first work out example 2.1 from Griffiths. So here what we are asked to do is we are given a line segment. So we have a line segment and this has a length of 2L. So this is 2L. Length. So we're going to consider it as if it is extending from minus L to plus L for symmetry. And we are supposed to find what the electric field is at a point above the midpoint of the line charge. So this is the midpoint of the line charge, and we are asked to find what the electric field is at this point P. So to do this, remember that we can consider this line charge as if it's made up of several tiny point charges. So I can write this as a tiny element dx and sum over all these charges to get the net electric field. So if I label this middle point as x is equal to 0 and this is dx, suppose this line charge has charge density. The charge density is, let's say, lambda. Then the charge in this small tiny part would be lambda dx. So then if I want to calculate what is the electric field coming from this tiny point charge at point P, obviously it'll be pointing along the line connecting these two. So this would be the direction, right? But if I want to find out what the magnitude is, I can write the electric field magnitude coming from this tiny charge as K times the charge. It's remember that it is k cubed by r squared, so we're going to write it as k, and the charge on this tiny element is lambda dx. And if this is r, we need to find r squared. But now look at this nice triangle here. Let's say this point P is at a distance z above the line, and let's say this element is at a distance x. And we're calling it at a distance x because our intention is to vary this. So we will take this charge first. So we have the line charge. So we'll start from this end, take a little dx, right, and then move to the next one, dx2, right, then next thing dx3, so on and so forth. We're going to sum over across the length of the charge. So that's why we're giving it symbol x here. And then so from this right angle triangle, then I can write r as x squared plus z squared, right? So then I would have x squared plus z squared. This is the one that is coming from one particular charge here, one particular point charge, which is we're considering to be of dx. And we're calling it, we're saying point charge repeatedly because our intention is to ultimately take this dx to 0 through a mental construct of completing the limit actually. But now every time in electric field and in general in these courses, you have to look at the inherent symmetry and make use of the symmetry here. So now if I look at the other end, if I were to take an element here, right, of the same length, let's say dx, then the field from this element would be pointing this way, right? So if I were to call this angle as theta, and same thing here, this angle is theta, then you see that if I look at the components of the green one would have a component this way and this way that is coming from the right end. Similarly, the red one would also have a component along this way and a component this way. So by symmetry, you see that as I am summing over, right, this segment and this segment at the two ends, they have some cancellation here. Only this vertical component survives. So if this angle is theta, this angle is theta, so this is the cosine theta component, and this is the sine theta component. So the cosine theta components cancel out, and you have only the sine theta components remaining. And because you have two such segments, overall you get a factor of 2 sine theta when you vectorially add those forces, or add those electric fields, sorry. And then we are going to just go from 0 to L, or minus L to 0, whichever way, so that because we are considering the symmetry of this, so we only need to integrate over the half of it, because we are combining one element at the right end, or one element at the left end, and one element at the right end. Both together give a component of this electric field that is, I'm going to call it E net, k lambda dx by x squared plus z squared times 2 sine theta. So this is, I'm adding the ones coming from the right side and the left side. So then I can see what sine theta is. Sine theta is from the triangle here, from this triangle here. I can see sine theta is opposite side by adjacent side. Sorry, opposite side by hypotenuse. So sine theta is equal to z over r. So that is equal to z over r is square root under x squared plus z squared. So therefore, the net electric field there would be k lambda dx by x squared plus z squared. I'm going to pull the 2 here up front, and then sine theta is this. So sine theta is z by square root of x squared plus z squared. Right. Now I can write this as 2k lambda z dx divided by x squared plus z squared whole to the power 3 by 2. But this is the net field coming only from the addition of the farmost left point and the farmost right point. If we want to get the same thing for all the elements, then we'll have to integrate to get E total. We have to go from 0 to L and integrate the net electric field that is a sum of a part on the right and a part on the left, right, along dx, right? So then we have 0 to L, E net was 2k lambda z dx divided by x squared plus z squared whole to the power 3 by 2. So if you do this simple integration, then you can take out 2k lambda z out, and then you have 0 to L dx over x squared plus z squared whole to the power 3 by 2. So that's easy enough to integrate. So you would get that integral as 2k lambda z. This integral, if I integrate 3 by 2, I add, this is x squared plus z squared to the power minus 3 by 2. So if I integrate and add 1, it becomes square root. So if I integrate that, I get x squared plus z squared minus 3 by 2 plus 1, right? And then I have the division, this itself, I'm going to get it as another x by z squared term because of the dx here, right? So then I can substitute the limit 0 to L here, and if I do that, I get this to be roughly k 2k lambda L divided by square root under z squared plus L squared times z. So the total electric field would be this, right? So if you take a point where z is much farther, right, then that is, you're taking this point to be very far away. Then if z is much greater than L, then E total is simply equal to 2k lambda L divided by z is much greater than L, so the z squared plus L squared is roughly z squared, so you would have in the bottom z squared, right? And in the case, if you think of a infinite line segment, a mental construct again, then you can substitute this limit with infinity and redo what the electric field due to such an infinite line of charge would be, right? And then figure out what you get. You would get something like E is equal to 1 over 4 pi epsilon naught 2 lambda by z, or this is essentially K. Okay, so now let's do another problem here where we are going to look at, let's look at a ring. So we're going to look at a ring of charge. So let's say we have a ring of charge. This is problem number 2.5 in Griffiths, where we have to find the electric field at a distance z from a circular loop of radius r. So this is the circular loop of radius r, and the distance is z, and we have to find the electric field at point P. So again, we look at the inherent symmetry, right? And do a similar thing like we did in the case of a line charge, except here now we have, if I take something on this side, let me call it small tiny charge dl, then there is electric field from this pointing along this way. Similarly, if I take on the opposite side another tiny charge here of the same length dl, then that would have a field pointing this way, right? So then again we would have, if you call this to be theta, then if you call this to be theta, then you would essentially have a component of the green and a component of the red survive, and the other components cancel out because the red one is pointing down and the green one is pointing up, right? So we have the cosine theta components now that survive. So if I now look at the electric field from this tiny little charge, so let's call that dE, from that tiny little charge at the top of the circular loop, that would be kq by kdq by r square. Let's call this larger r square, which is this, or let's do one thing here. Sorry, let's change the radius of the loop to capital R so that we can keep the distance r as a variable. So then I have here 2 r square, right? So the field coming from this top is kdq by r square, and dq is nothing but lambda dl again, where lambda is the charge density and dl is the length by r square. Similarly, from dE below, from this, also you would have a similar thing, kdq by r square, right? That would also be kdl by r square, but these are top and bottom. The fields coming from here and here are along 2 different directions. So this is pointing this way. The one at the bottom, the one at the top is pointing this way. So only the vertical components cancel out, and only the horizontal cosine theta component survives. So d net coming from these 2 tiny charges is equal to d top plus d bottom. That is in terms of vectors. These are only magnitudes. So if I add the vectors, essentially I would get a 2 cosine theta. So I would have k lambda dl by r squared 2 times cosine theta, 2 because the 2 components are getting added and only the cosine parts are getting added. So if this is theta, now let's draw this figure a little more clearly. So if this is the circular loop with radius r, and I'm looking at this angle theta here. That is the angle here, theta. So then that theta is, I want cosine theta, right? Cosine theta is adjacent side, which is z, right? And the hypotenuse, which is square root of r squared plus z squared, right? Because this is r and this is z. So then I can write this as k lambda dl 2k lambda dl by r square times z by square root under r squared plus z square, right? Again, this r is also similarly r squared plus z square. So I would get 2k again, just like the previous problem. I get 2k lambda dl z divided by square root under r squared plus z square. Oh, this would be 3 by 2, sorry. So now if I integrate this from if I integrate this over the circular loop, I essentially get the dl to be the circumference. So E total would be 2k lambda dl. If you go around the loop and calculate dl, you get a 2 pi r times z divided by r square plus z square whole to the power 3 by 2. And it is pointing along this direction, the z direction. So that is how we can calculate for a ring. Similarly, we can even calculate for a sphere. In fact, we have seen that by the same logic, in a sphere, if I have a sphere, the electric field inside the sphere is 0 because I can take one circular loop here, right? And if I look at any point inside the sphere, right, this circular loop would have, net field this way. And similarly, if I look at another circular loop that is diametrically opposite, then that would have equal and opposite electric field pointing the other way, coming from this, from two circular loops within the sphere, within the green sphere. So the electric field inside the sphere, as we have seen, is equal to 0. And outside it behaves like a point charge, right? So you would have at any point here, right? You would essentially have kq by, if this is at a distance z from the center, you would have kq by z square, where q is the total charge. So you can treat a sphere like a point charge. I'll assign this. This is problem number 2.7, which I will assign as homework, so you can actually do the integral and see. So to do that, you will need to take the sphere. So and then draw the xyz axis, and you would start out from one point which is at a radius r, right, and take a small area element, right, and calculate the field from this small area element at the point P, right, and then integrate all over the sphere to get the net electric field. So this I will assign as a homework problem so that you can see how a sphere behaves like a point charge. So these are some ways to calculate the electric field, and I just wanted to do these couple of examples for now so that we can get started on solving problems with electric fields and potentials.